So far, we have talked about atoms of different chemical elements, the building blocks of ordinary matter, and about chemical compounds that are made by combining atoms of different types into well-defined arrangements at well-defined ratios. The number of chemical elements is relatively large, and 94 of the 118 elements known today occur naturally on Earth. Consequently, there is a significant number of elemental substances that are built from atoms of just a single element, especially considering that different arrangements of atoms of the same chemical element result in the formation of different allotropes that can have very different properties. For example, graphite and diamond are two allotropes of the same chemical element, carbon. However, the number of chemical compounds produced by combining atoms of more than one element by far exceeds the number of elemental substances. Chemical compounds, such as water, sugars, lipids, amino acids, and nucleic acids, are essential to the existence of living organisms. Other chemical compounds, such as polymers, ceramics, binary semiconductors, and organic solvents, are at the foundation of modern technology and make up many of the objects around us: fabrics, paints, plastics, electronic devices, etc. At this point, we have already learned about the composition of various chemical compounds. For instance, we know that compounds that contain atoms of a metal and one or more nonmetals are ionic, and that compounds that contain atoms of nonmetals only are usually molecular. We have also discussed how the composition of a compound can be determined experimentally in the lab. However, we haven't talked in any detail yet about the processes by which atoms of different elements are combined in specific ways to form chemical compounds. These processes, known as chemical reactions, will be the focus of the third segment of our course. Learning about them is extremely important because chemical reactions are what really makes chemistry useful. Understanding how they occur allows us to devise recipes for breaking up a substance into atoms that make it up, then combining those atoms with atoms that come from another substance to make new substances with desired properties. In a chemical reaction, atoms of one or more compound are used to build one or more other compound. We have actually already seen chemical reactions in this class, although we haven't used this term to refer to them. For instance, in the video about determining the empirical formula of a chemical compound experimentally, we determined the formula of a metal oxide as follows. We first weighed a piece of metal, then heated it in air until it turned into a white powder, then we weighed the white powder, and found that its mass was greater than the mass of the metal that we started with. We explained this finding by saying that the white powder was a metal oxide that formed by attaching oxygen atoms taken from the air to metal atoms. The extra mass was therefore the mass of the oxygen added to the metal, and we determined the number of moles of oxygen atoms per number of moles of metal atoms to find the empirical formula of the oxide. The process that we just described is in fact nothing else than a chemical reaction. We started with two different substances, in this case elemental substances, the metal and oxygen, and formed a new substance, the metal oxide. This process can be schematically represented as follows. We take some metal, add some oxygen, heat it, and we get the oxide. This schematic representation of a chemical reaction is called the equation of the chemical reaction, or simply a chemical equation. To the left of the arrow in the chemical equation, we have the substances that we start with, called reactants. In the examples that we are considering, the reactants are a metal and oxygen. To the right of the arrow, we have the new substances that we get after performing the chemical reaction, called the products. In our example, we only have one product, the metal oxide. Above or below the arrow, we indicate what needs to be done to the reactants in order for the reaction to occur, the reaction conditions. In some cases, simply combining the reactants leads to the reaction occurring spontaneously. In those cases, reaction conditions do not have to be specified. However, in many cases, when the reactants are mixed together, the reaction may occur very slowly or it may not occur at all. In order to bring about the reaction or accelerate it, one may need, for instance, to heat the mixture of reactants or expose it to light or bring it in contact with a catalyst, a substance that accelerates a reaction when it is present in the reactant mixture without being used up itself. In such cases, a note should be made above or below the arrow in the chemical equation, what the required conditions are. Often special symbols are used to summarize the reaction conditions. Here are some examples of such symbols. The Greek capital letter delta, that looks like a triangle, means that the reactants must be heated. A temperature indicated above or below the arrow, such as 100 degrees Celsius, means that the reactants must be heated to the specified temperature. The letter H followed by the Greek letter nu means that the reactants need to be illuminated with light. The word reflux means that the reactants must be continuously heated to boiling and the vapor should be then recondensed. A chemical formula means that the reaction should be performed with the specified chemical either as a catalyst that should be present or the solvent in which the reaction should be performed. A time, such as 3 hours, indicates that a chemical reaction must be carried out over the specified duration. This list is non-exhaustive, although these are some of the more common reaction conditions that you may see. Other reaction conditions could be specified as well. So let's write down an example of a chemical reaction, namely the reaction of forming magnesium oxide by heating magnesium in the presence of atmospheric oxygen. To the left of the arrow, we have the reactants: magnesium metal that is made of magnesium atoms, Mg, and oxygen gas that is made of diatomic oxygen molecules, O2. To the right of the arrow, we have the product, magnesium oxide, an ionic compound that consists of magnesium and oxygen atoms at a 1-to-1 ratio and therefore has the empirical formula MgO. After each of the reactants and products, we specify its aggregate state in parentheses. In the chemical reactions that we will be considering in this class, you will see 4 different aggregate states of reactants and products specified. Solid, specified by the letter S, liquid, specified by the letter L, gas, specified by the letter G, and aqueous solution, specified by the letters AQ. In the gas state, a substance maintains neither its shape nor its volume. Atoms or molecules that make up a gas fly around freely throughout any container that the gas is kept in. If you pump air into a tire, you compress greater and greater amounts of air into the volume of the tire, and if the tire pops, the air comes out of it and spreads throughout the atmosphere. In the liquid state, a substance maintains its volume but not its shape. For instance, if we measure 100 milliliters of liquid water in a graduated cylinder and then transfer it to a flask, the water will take the shape of the new container, but we will still have the same volume of it, 100 milliliters. In the solid state, a substance maintains both its volume and its shape. Finally, an aqueous solution is a substance that is dissolved in water. The substance that is dissolved, known as the solute, can be ionic, such as table salt, or molecular, such as sugar. However, not all substances dissolve in water. Examples of substances that don't are oil or gold. Note that an aqueous solution of a substance is not the same as the liquid state of the substance. The liquid state of a substance consists entirely of atoms or molecules of that substance. In contrast, the aqueous solution of a substance primarily consists of water molecules, with some atoms or molecules of the substance dissolved in it. For instance, if you place a teaspoon of sodium chloride, table salt, into a glass of water, you will get an aqueous solution of sodium chloride. On the other hand, if you heat sodium chloride to temperatures higher than its melting temperature, 1473.3 degrees Fahrenheit, you will get liquid sodium chloride. We will talk more about aqueous solutions in the next lectures. It is important to specify the aggregate state for each reactant and product in a chemical reaction. Although we typically know the aggregate states of elemental substances and chemical compounds at room temperature and normal atmospheric pressure, under other conditions, the states of the same substances can be different. For instance, water is a liquid at room temperature, but at temperatures below 32 degrees Fahrenheit it becomes a solid, ice, and at temperatures above 212 degrees Fahrenheit it becomes a gas, water vapor. Another example is all metals, except mercury, are solid at room temperature, but they can be melted and become liquid at high temperatures. Note that the transformations between solid, liquid, and gas states, as well as the dissolution of a substance's water, are physical, not chemical changes. No chemical reactions occur in such transformations. For instance, ice, liquid, water, and water vapor are all made of the same molecules, H2O. In contrast, as we said earlier, in a chemical reaction, substances are broken apart into atoms, and these atoms are combined in some new way to form new substances. Coming back to the chemical reactions that we have been considering, the formation of magnesium oxide from magnesium metal and atmospheric oxygen gas. We see that one of the reactants, magnesium, and the product, magnesium oxide, are both solid, and the second reactant, oxygen, is a gas. The Greek capital letter delta above the arrow that points from the reactants to the products indicates that the reactants must be heated in order for the reaction to occur within a reasonable time. At this point, we have talked about all components of the chemical equation, except one. We said that on the left-hand side we have the chemical formula of the reactants, and on the right-hand side we have the chemical formula of the products, that following these formulae in parentheses, we indicate the aggregate states of the reactants and the products, and that above the arrow that points from the reactants to the products, we specify the reaction conditions. The only thing we haven't discussed yet are the coefficients 2 in front of the chemical formula of magnesium and magnesium oxide. These are so-called molar ratio coefficients. They indicate how many atoms or molecules of each reactant must be taken in order to completely use up all reactants, and how many atoms or molecules of the product will be formed as a result. In the examples that we are considering, one must take 2 magnesium atoms and 1 oxygen molecule. If the coefficient before a reactant or product is 1, it is omitted. Then we can use the 2 magnesium atoms and the 2 oxygen atoms that make up the diatomic oxygen molecules to make 2 smallest units of the magnesium oxide that consist of 1 magnesium atom and 1 oxygen atom each. No magnesium or oxygen atoms will remain unused. We will talk more about determining these coefficients in chemical reactions, and we'll see why it is useful to know them in upcoming videos.